to Tungal online classes. In the last class we completed the work done by the frictional force whenever the block is placed on the horizontal surface. Now we are going to discuss the amount of work done in the case of the inclined planes. So in that the first one is a body of mass m is sliding down on the smooth inclined plane of inclination theta. If L is the length of the inclined plane, the work done by the gravitational force is Which type of inclined plane they consider here? They consider the smooth inclined plane. So whenever the body will be sliding on the smooth inclined plane, the force which is acting on the body is nothing but gravitational force. So that while the body will be sliding downwards on the moving body, which type of force will be acting here? Gravitational force. So here the component of the gravitational force is equal to mg sin theta. The component of the gravitational force which is acting on the sliding down body on the smooth inclined plane is nothing but what? F gravitational is equal to mg sin theta. Here they mentioned that capital L be the length of the inclined plane. So that the displacement covered by the body is equal to what? Capital L. So what is the work definition? Work done is equal to force into displacement into cos theta. See here, the displacement will be in the direction, the downward direction, and the component of the gravitational force is also acting in the same direction, so that here the angle between the gravitational force and displacement values are 0, so that the work done by the gravitational force is equal to What is the magnitude of the force? mg sin theta, and displacement magnitude is equal to L, and theta value 0, cos 0 degrees. So this value becomes to what? mgl sin theta. So this is the amount of work done whenever the body will be sliding downwards on the smooth inclined plane. So this is the first application regarding the inclined plane concept. The next application, a body of mass m is moving upward on the smooth inclined plane of inclination theta and length L by a constant horizontal force of capital F. So in this case, over the sliding down body there is no external force will be acting, and it is sliding down due to the component of the gravitational force only, In the second application, it is also related to smooth inclined plane. So here over the given smooth inclined plane, an object will be placed. Whenever the object will be placed on the smooth inclined plane, always mg sin theta will be acting in the downward direction. Whether the given plane will be the smooth inclined plane or rough inclined plane, mg sin theta component is always acting down the plane. Now what they are saying that over this given body, we are applying the constant force. In the upward direction. With the help of the application of the external force, the motion of the body will be in the up the plane. So the motion of the body in the second case will be what? It is moving up the plane. And what they are asking that if L is the length of the given inclined plane, work done by the resultant force. See here, already you know the free body diagram. It is the pulling force, it is the opposing force. What is the resultant force acting on the block? F resultant is equal to pulling force, F minus opposing force is equal to what? mg sin theta. So in this case, whenever the body will be moving up the smooth inclined plane, net force acting on the sliding body is equal to what? F resultant is equal to F minus mg sin theta. Now they are asking what? Work done by the resultant force. Work done by the resultant force is equal to what? F resultant into displacement into cos theta. See here, the resultant force will be acting up the plane. F resultant will be acting up the plane, and the displacement of the object is also in the up the plane. So that theta value is equal to 0. Directly we will write cos theta value is equal to 1. Therefore, work done by the resultant force is equal to work done by the resultant force is here. Theta value is equal to what? 0. Since net force will be acting up the plane and also displacement is also acting in the upward direction. Work done by the resultant force is equal to what? What is the resultant force magnitude? F minus mg sin theta. F minus mg sin theta. Displacement is equal to L cos theta value 1. Therefore, work done by the resultant force is equal to F minus mg sin theta into L. So, this is the work done by the resultant force. So, work done by the resultant force whenever the body was moving up the plane along the smooth inclined plane. Along the smooth inclined plane. Related to what? Rough inclined plane. This application related to what? Rough inclined plane. See here. A body of mass m is placed on the rough inclined plane, and they are saying that the angle of inclination is equal to theta. If L is the length of the incline and mu k is the coefficient of kinetic friction, the work done by the resultant force on the body. Here, which type of inclined plane we consider here? Rough inclined plane. Whether you consider the plane will be either smooth inclined plane or rough inclined plane, first we have to represent the gravitational component of the force which is acting along the inclined plane. So, the component of the gravitational force which is acting along the inclined plane is always equal to what? Mg sin theta. Here they specified that the given inclined plane will be the rough inclined plane. Given inclined plane is what? Which type of plane? Rough inclined plane. So that the motion of the body, they mentioned that it is moving down the plane. So that the body will be sliding downwards. Whenever the body will be sliding downwards, frictional force will be acting up the plane. In this case, they are asking that work done by the resultant force. First, you write the resultant force here. F resultant is equal to, the resultant force is always existed in the direction of the motion. Since the motion will be in the downward direction, resultant force is equal to mg sin theta minus fk. Already you know that frictional force is equal to mu k into n, that value is equal to mu k mg cos theta. This formula already we know in the case of the friction. So that directly I am writing that mg will be the common factor sin theta minus mu k cos theta. This is a what? Resultant force acting on the body which is moving in the downward direction. So they are saying that if L is the length of the inclined plane, then work done is equal to, what is the formula? Work done is equal to F resultant into displacement. What is the F resultant value? Mg into sin theta minus mu k cos theta, and the displacement value is equal to what? L. So directly theta value will be what? 0. So cos theta value is equal to what? 1. Therefore, work done by the resultant force is equal to mgl into sin theta minus mu k cos theta. So this is the expression for work done by the resultant force whenever the body was sliding down the rough inclined plane. So whatever the case they mentioned, first we have to calculate what is the resultant force acting on the block. If it is moving in the downward direction, mg into sin theta minus mu k cos theta. If it is moving upward direction, mg into sin theta plus mu k cos theta. So that we have to consider the situation. So in that we have to first calculate the resultant force. Okay, next. Another application they given, fourth one. Next, see the application number 4. Here they consider a uniform solid cylinder of mass m, length L and radius r is lying on the ground with the curved surface in contact with the ground. See here, the same cylinder will be taken in two different cases. In the first case, the curved surface of the cylinder will be in contact with the ground. So they mentioned that it is which type of cylinder? Uniform cylinder. Uniform cylinder. In the last class I told, whenever you take either uniform rod, uniform rope, uniform thread, which type of physical quantity we have to consider? Center of gravity of the given uniform object. Since the cylinder will be the uniform cylinder, first we have to locate its center of gravity. The center of gravity will be at a height of small r from the ground. Center of gravity will be at what height with respect to the ground in the initial case? The center of gravity will be at a height of a small r with respect to the ground whenever the curved surface will be in contact with the ground. Now, by applying some external force, we make it vertical. Whenever we make it vertical, the center of gravity position will be existed at its geometric center only. Center of gravity position does not be changes, that will be existed at the center of gravity. If you look at this diagram, whenever you make the cylinder will be the vertical position, since its total length value is equal to small l, so that in this case, in its vertical position, the height of the center of gravity again from the ground is equal to what? L by 2. Already I told, whenever you are going to calculate work done in the case of the center of gravity, you have to follow the formula work done is equal to mg into h suffix cg. What is the h suffix cg? Height raised by the center of gravity. If you look at the diagram, the dotted line will be indicating the initial position of the center of gravity. The dotted line is really indicating what? Initial position of the center of gravity, and so this is the final position of the center of gravity. So here I mentioned that h will be indicating what? Height raised by the center of gravity. See here, from here to here the value is equal to small r. From here to here this value is equal to small h, and this total length value is equal to what? L by 2. From the given diagram I will write h plus r is equal to L by 2. H plus r is equal to what? L by 2. What is the h here? Height raised by the center of gravity. From this, h value is equal to L by 2 minus r. H value is equal to what? L by 2 minus r. What is the L by 2 minus r? Is indicating that the height raised by the center of gravity due to change in the position of the uniform cylindrical rod. Therefore, work done is equal to formula mg into, in the place of h what we have to write? L by 2 minus r. Work done is equal to what? Mg into L by 2 minus r. Like this we have to calculate the work done in the case of the uniform cylindrical rod. Done by the gas. So in thermodynamics, you know very well about a cylindrical vessel we consider and a smooth piston we consider there. So here also I consider a cylindrical container will be taken. For that cylindrical container we taken one frictionless movable piston. So inside the container I am assuming that some gas will be present. So whenever we supply some extra energy to the gas which was present within the container, that gas going to be expands. So whenever the gas is going to be expands, these gas molecules are exerting some upward force over the surface of the frictionless piston. So here I am assuming that the pressure of the gas is equal to what? Capital P, and the surface area of this piston is equal to what? Capital A. So what I am assuming that let P will be indicating the pressure of the gas which was filled within the cylindrical vessel, and the area of cross section of the given piston is equal to what? Capital A. So from the definition of the pressure, pressure is equal to force acting per unit length. From this I am taking the expression for the force, so that the force applied by the gas is equal to the force applied by the gas molecules on the piston is equal to what? F is equal to P into A. P into A. How can we take the force value here? We know that the gas molecules are existing some pressure value. That pressure will be defined as a what? Force per unit area of cross section. I am assuming that the area of cross section of the piston is equal to capital A. By the definition of the pressure is equal to force upon area. From this side, force is equal to what? P into A. So that by the definition of the force, whenever we apply some external force over the given object, it will cause some displacement. Similarly, here also, whenever the gas molecules are exerting some force over the given piston, the piston will be displacing from the point x to y by the displacement of dx. So the displacement produced within the piston is equal to what? Displacement S is equal to what? Dx. Displacement S is equal to what? Dx. Therefore, work done is equal to force into displacement. Work done is equal to what? Force into displacement. Force value is equal to what? P into A and dx. And dx. See here. Pressure of the gas will be constant. Pressure of the gas will be constant. Area into displacement, that is nothing but a change in volume. That is nothing but what? Change in volume. So therefore, for the small amount of the volume, for the small amount of the change in volume, the work done will be taken as a dW. Therefore, work done for a change in volume, for the work done for a change in volume is equal to what? dW is equal to P into dV. dW is equal to what? P into dV. Suppose if you want to change the volume from V1 to V2, you have to integrate. Therefore, total work done is equal to integral of V1 to V2 P dV. Integral of V1 to V2 P dV. So here the pressure of the gas will be constant. Integral dV limits from V1 to V2. Therefore, if you integrate this one, you will get the total work done is equal to what? P into V2 minus V1. P into V2 minus V1. Like this, we have to calculate the work done by the gas whenever you taken in a given cylindrical container. So that is the another application. Next application is the what? Pulley concept. Already we discussed this concept in Newton laws of motion. There what we derived? Whenever two blocks of masses m1, m2 will be connected with the help of the light string, and that string is passing over the smooth pulley, and if the blocks are came into the motion, you calculate the acceleration produced in the system as well as tension developed within the string. So here also I consider the same concept. I consider the two blocks having the masses of m1, m2, and initially they will be released. From the same horizontal level. Initially both the blocks are released from where? Same horizontal level. Whenever both the blocks are released from the same horizontal level, its weight m1g will be acting in the downward direction. Its weight m2g is also acting in the downward direction. Since m1 will be the heavier block, that's why it is moving in the downward direction. m2 will be the lighter block, that's why it is moving in the upward direction. I am assuming that in a time of t seconds, at t is equal to 0, they will be released, and in a time of t seconds, the m1 block will be reaches here by covering the displacement of x. At the same time, the m2 block is also covering the same amount of displacement x in the upward directions. So what is the x here? So x will be indicating the displacement covered by both the blocks m1, m2 in a time of t seconds. m1 will be covering the displacement in the downward direction, m2 will be covering the displacement in the upward direction. So I want to calculate work done by the gravitational force for the first block as well as the second block. So I want to calculate work done for the first block is equal to work done by the gravitational force for the first block. Gravitational force is acting in the downward direction for the first block, and the displacement is also in the downward direction. So that directly I am writing work done by the gravitational force for the first block is equal to, I put plus m1g into x. Plus is indicating that both the force as well as the displacement are in the same downward direction. Now coming to the second block, work done by the gravitational force for the second block. Gravitational force will be in the downward direction, displacement will be in the upward direction, theta value is equal to 180, so that its work done will be the negative. So that directly here I am writing that W2 is equal to minus m2g into x. Why put the minus here? If you want to write fs cos theta, f is m2g, displacement x, theta value cos 180 is equal to minus 1. Directly I wrote W2 is equal to what? Minus m2g into x. Total work done is equal to, always we have to take the algebraic sum of the individual work dones. Total work done is equal to W1 plus W2, that value is equal to m1gx minus m2gx. So here m1 minus m2 into gx. Total work done value is equal to what? m1 minus m2 into g into x. What is the x there? Displacement covered by the object either in the downward direction or in the upward direction in a time of t seconds. Already we know that whenever the blocks are released, they will be traveling with the same acceleration. That acceleration value will be given by acceleration A is equal to m1 minus m2 into g by m1 plus m2. m1 into m1 minus m2 into g by m1 plus m2. This is the expression for acceleration acquired by the each block, or with what acceleration the blocks are moving, that is given by m1 minus m2 into g by m1 plus m2. Now, I want to calculate the distance. See here, I told this block will be released means of what? Initial velocity is equal to 0. Initial velocity what? 0. Therefore, displacement s is equal to ut plus half at square. So, initial velocity is equal to 0. Therefore, displacement value will be taken as x. X is equal to half into a into t square. Half into, what is the value of a? m1 minus m2 by m1 plus m2 into g into t square. So, this is the expression for the displacement covered by the each block either in the downward direction or in the upward direction. If you substitute this x value here, if you substitute that x value there, so you will get total work done is equal to half will be the constant, half into here m1 minus m2 will be there, here also m1 minus m2 will be there. In the numerator, m1 minus m2 whole square by, in the denominator one m1 plus m2 will be there, m1 plus m2. Here one g will be there, here also one g will be there. So that g into g square, so t square will be there. So this is the final expression for the total work done in the case of the pulley block system. So the next concept, energy. Up to now we completed the work in different cases. Now we are going to discuss about the energy. How many types of energy we have on this topic means we have two types of energies. The first one is about kinetic energy and the second one is about potential energy. Already you know the basic definition of the kinetic energy. What is the basic definition of the kinetic energy? The energy possessed by a body by virtue of its motion will be calling as what? A kinetic energy. What is the general formula for the kinetic energy? The general formula for the kinetic energy will be given by kinetic energy Ke is equal to what? Half into m into v square. What is the general formula for the kinetic energy? Half into m into v square. This energy will be possessed by the bodies which are to be in the motion. If you consider any one of the moving object, it will be having some kinetic energy. Whenever the object will be having some kinetic energy, it is also having one more physical quantity, that is nothing but linear momentum. If you consider any one of the moving object, if it is having the kinetic energy means it is also having some linear momentum. What is the basic formula for the linear momentum? Linear momentum P is equal to what? Mass into magnitude of the velocity or speed. So that linear momentum P is equal to what? M into V. Now, what is the relation between kinetic energy and linear momentum? What is the relation between the kinetic energy and linear momentum? The relation between the kinetic energy and linear momentum will be given by Ke is equal to P square by 2m. If the momentum of the object will be constant, if a momentum will be constant, kinetic energy is inversely proportional to the mass. Kinetic energy is equal to what? Inversely proportional to the mass whenever the momentum of the system will be constant. Now we will see two applications are there. In that the first application is the what? Gun bullet system. So before firing the bullet from the given gun, the initial momentum of the system is equal to 0. According to the law of conservation of linear momentum, the final momentum is also to be equal to 0. Already this was we studied in the Newton's laws of motion. So whenever you consider the gun bullet system, before firing the bullet, the initial momentum of the system is equal to 0. As a result, the final momentum of the system also to be equal to what? 0. So now we are considering this relation. What is the relation here? Kinetic energy Ke is equal to, kinetic energy Ke is inversely proportional to mass, or directly we will writing that kinetic energy K is equal to P square by 2m. So here the momentum value will be remain same, so that I will write kinetic energy is inversely proportional to the mass. Kinetic energy is inversely proportional to the mass. Now I want to calculate the ratio of kinetic energy of the bullet to the kinetic energy of the gun. So that I will write kinetic energy of the bullet to the kinetic energy of the gun is equal to. So kinetic energy is inversely proportional to the mass means, so I will write here mass of the gun by mass of the bullet. Mass of the gun by mass of the bullet. Kinetic energy is inversely proportional to the mass, so that kinetic energy of the bullet by kinetic energy of the gun is equal to mass of the gun by mass of the bullet. So this is the first application which is related to the kinetic energy of the system. And the second application, a bullet of mass m is moving with a velocity v, stops in a wooden block after penetrating through a distance x. If S is the resistive force offered by the block of the bullet, then see here they consider a wooden block. They consider what? A wooden block they consider like a target, We are firing the bullets, with the help of the gun, While the bullet will be reaching the target, its initial velocity is equal to u. What is the u here? The initial velocity of the bullet just before entered into the target. U is indicating what? Initial velocity of the bullet just before entered into the target. So whenever it is entered into the target, it will be traveled some distance and it was finally coming to the state of the rest. So what they are saying that on the bullet, the wooden block will be applying some resistive force. As a result, the bullet will be traveled some distance x and then finally it is coming to the state of the rest. Then they are asking what is the magnitude of the resistive force that is offered by the target. So to calculate the resistive force which is applied by the target, I am following the work energy theorem. What is the work energy theorem? Work done is equal to change in kinetic energy. Work done is equal to what? Change in kinetic energy. See here, the resistive force will be acting towards the left, displacement will be towards right. So that work done is equal to resistive force, displacement into cos theta, that is equal to. Finally, it is coming to the state of the rest. So that final kinetic energy value is equal to 0. Final kinetic energy value is equal to what? 0 minus initial kinetic energy is equal to half mu square. Here, the angle between the resistive force and displacement will be 180. So that cos theta value will be minus 1. So therefore, minus f into displacement will be x. Cos theta value is equal to what? Minus 1. Already we wrote the minus earlier. So minus f into x is equal to what? Minus half mu square. Minus getting cancelled. Therefore, f is equal to mu square by 2x. F is equal to what? Mu square by 2x. So that is the expression for the resistive force which is offered by the given torque or given wooden block. So this is the expression for the resistive force that is offered by the wooden target. Potential energy. Already we know the definition of the potential energy. What is the definition of the potential energy? The energy possessed by a body by virtue of its position will be calling as a what? Potential energy. The another definition of the potential energy is also there. That is the work done by a conservating force. The work done by the conservating forces will be stored in the form of a potential energy. What is the another definition for the potential energy? The work done by the conservative forces, will be stored in the form of a potential energy in the respective bodies. So what are the conservative forces? What are the examples for the conservative forces? The examples for the conservative forces is gravitational force, second one is a what? Spring force, and the third one is a what? Electrostatic force. So what are the examples for the conservative forces? Gravitational forces, spring forces, and electrostatic forces. Whenever these type of gravitational, spring force and electrostatic forces are doing some work done, this work done will be stored in the form of a potential energy. This is the another definition for the potential energy. So the relation between conservative forces and its potential energy will be given by F is equal to what? Minus du by dr. F is equal to what? Minus du by dr. Here u will be indicating the potential energy. U will be indicating what? Potential energy. This formula will be applicable for which type of forces only? That formula will be applicable for only conservative forces only. For which type of forces? Conservative forces. Now I want to calculate the work done. So that I cross multiply this. So work done is equal to dw is equal to F into dr. F into dr, that value is equal to minus du. So work done formula, generally we know that work done is equal to force into displacement. Force into displacement is equal to what? Minus du. From this I will write du is equal to minus F into dr. Du is equal to what? Minus F into dr. If you are integrating on both sides, you will get the total potential energy value. The total potential energy is equal to minus integral F bar dot dr bar. Minus of integral F bar dot dr bar. By using this relation, we will be calculating the potential energy for conservative forces. Potential energy for conservative forces. Next one. Gravitational potential energy. Gravitational potential energy. See here, I am assuming that a block of mass m, will be placed on the horizontal surface. A block of mass m will be placed where? On the horizontal surface. By applying some external force, if this block will be lifted, through a height of small h, whatever the work done by the external force, against the gravitational field, will be stored in that body, in the form of a potential energy. Once again, here actually the block will be placed where? On the horizontal surface. By applying some external force, this block will be lifted to a height of small h. For that purpose, we are doing some external work done. Which is against the gravitational field. Why? The gravitational field will be acting in the downward direction, so that you have to do the work done against the gravity. So this, whatever the work done will be done by the external force, that work done value will be stored in this body. In the form of a gravitational potential energy. So that the work done by the external force is equal to what? F external into displacement. Here the magnitude of the external force applied, that is applied over the body, will be equivalent to weight of the given body. So that the external force of magnitude will be is equal to mg. The external force of magnitude is equal to what? Mg. And what displacement it was lifted means h. Therefore work done by the external force is equal to what? Plus mgh, which is stored in the form of a potential energy, body as potential energy. So this is the expression for gravitational potential energy. Next application, work done by a spring force. It's a very, very important application. See here. So for this we consider one spring which is placed along the horizontal direction. One end of the spring is connected to the vertical wall, another end of the spring is connected to a block of mass m. So initially I am assuming that the length of the spring is equal to, initial length of the spring is equal to L naught. What? L naught. Whenever we didn't apply any external force, over the given spring, the length of the spring is equal to what? Constant. Here I attached a block of mass m to the free end of the spring and I want to pull the spring outwards. I want to elongate the spring or I want to compress the spring. So, whenever we are going to elongate the spring, the length of the spring value will be changes. The length of the spring value will be changes. So, whenever we want to displace the object from its equilibrium position, within the object, some restoring forces are developed. Which type of forces are developed? Restoring forces. Like a simple pendulum, we know that whenever the pendulum will be displaced like this, and if you release the pendulum bob, so it will be coming towards the mean position with the help of the restoring force. What was developed within the pendulum bob. Similarly, whenever you want to pull the spring, within the spring, some internal forces, some restoring forces are developed. The restoring forces within the spring will be calling as the word spring forces. The spring force magnitude is equal to the spring force. The spring force is represented by Fs, that is equal to what? Minus Kx. Spring force formula is equal to what? Fs is equal to minus Kx. Just now only we told spring forces are the conservative forces. Spring forces are what? Conservative forces. Here the negative sign is indicating what? Whenever we are elongating the spring, the displacement direction will be acting towards the right side direction and restoring force will be acting towards the left side direction. So that the direction of the restoring force is always opposite to the direction of the displacement, so that the restoring force Fs will be given by minus K into x, where x is the elongation and K is the spring constant. Just now only we defined the work done by the conservative forces. Work done by the conservative forces will be stored in the form of the potential energy. Work done by the conservative force will be what? Stored in the form of a potential energy. See here, which force here we consider a spring force? Already we told this force is a what? A conservative force. I am assuming that whenever we apply some external force, I want to elongating the spring. So, with the help of the external force, I am assuming that the spring is elongated by a displacement of dx. So, what is the dx here? The elongation produced in the spring, due to the external force which is acting over it. But here we want to calculate work done by the conservative forces. So here, for the small amount of the displacement of dx, the work done will be taken as a dw. So here, dw will be indicating what? Work done by the conservating forces. What is the conservating force? Restoring force, displacement S, and a theta value is equal to what? Theta value is equal to cos theta. See here, F restoring S into cos theta means here F restoring will be indicating the magnitude of the restoring force. S is indicating what? Magnitude of the displacement, and theta is indicating what? Angle between restoring force and displacement. That angle value is equal to what? 180. The angle between the restoring force and the displacement is what? 180 degrees. Now, work done by the conservating force is represented by dw for the small amount of the displacement. So, conservative force magnitude kx and the displacement is equal to dx cos 180 minus 1. Therefore, dw is equal to minus kx into dx. Now, I want to calculate the total work done for the elongation of x. Therefore, for getting the total work done, simply we have to do the integration. So that here minus kx dx. Again, k will be the constant. Integral x dx. Integral x dx is equal to formula, that is equal to what? X square by 2. Therefore, total work done is equal to minus half kx square. Total work done value is equal to what? Minus half kx square. This is the work done by which force? Conservative force or spring force? By the definition of the potential energy, what we told, work done by the conservative forces will be stored in the form of the potential energy. Therefore, potential energy which is stored inside the spring is equal to, that value is equal to what? Minus half kx square, minus half kx square. Generally, the potential energy is represented by U. U is equal to minus half kx square, minus half kx square. So, this is the expression for potential energy of a spring. Sometimes they are asking that, what is the work done? What is the work done for elongating the spring? For elongating the spring from x1 to x2. What is the work done is required in elongating or compressing the spring from x1 to x2. How can we calculate this value? Now we will see. Initially, what is the elongation of the spring x1? So that I will write the initial potential energy of the spring. Initial potential energy of the spring, U suffix I is equal to minus half into k into x1 square. Minus half into k into x1 square. What is the final elongation value? x2. Therefore, final potential energy value is equal to minus half into k into x2 square. x2 square. What is the work energy theorem? Work done is equal to change in kinetic energy. So, we will also write work done is equal to change in potential energy. Change in potential energy for the conservative forces. So that for conservative forces, work done value is equal to change in potential energy. Change in potential energy. Therefore, W is equal to final potential energy minus half into k into x2 square, minus half minus plus. So, initial potential energy value is equal to what? Half into k into x1 square. From this we will write half into k will be the common, x1 square minus x2 square. So, this is the expression for work done in elongating the spring. Work done in elongating the spring from initial elongation x1 to the final elongation x2. It is the concept of work done by the spring. So, it is a very important concept. Okay. Thank you.